Right, hello everyone. We're back to the next lecture of aircraft flight mechanics. We're looking at the next part of the final part of aircraft performance. So everything we've done so far has been with the aircraft in steady level flight. So we have got equilibrium of all forces on the aircraft. And what we're going to start looking at now is aircraft acceleration. Now, we're not talking about acceleration as in getting faster, speeding up. We're talking about accelerated flight whereby the forces are constant on the aircraft, but they're not a net zero. So we're looking at a means that we can define how to quantify those loads, and we're going to look at then a couple of simple maneuvers. So we're going to look at loops, two different sorts of loops. We're going to look at constant radius loops. We're going to look at constant load factor loops. So we need to define what the load factor is. And then we're going to look at steady turns in the horizontal plane. So before we move ahead with that, we're going to talk about load limits on the aircraft. So our aircraft are flying along, and again in equilibrium flight we've got the lift is equal to the weight. So lift equals weight, that's our equilibrium steady flight condition. If we want to move into a turn or into some sort of circular arc maneuver, i.e. a loop or a pull-up, then the lift on the wings needs to be increased. So we define the increase in lift by something called the load factor. The load factor is simply the lift that's being produced divided by the weight. So let's move over to the iPad and we can start to define some of these things. So that's our first definition. We've got the load factor. And this has the symbol N. Again, in aeronautics, we tend to reuse symbols for lots of different things, which might start to irritate you a little bit because N will later on be the yawing moment. But for now, it's the lowercase n is our load factor. So N is defined as the lift divided by the weight. Okay, so this is the lift that's being produced. And then on the bottom we just have the weight of the aircraft. So we can probably appreciate that in steady level flight N has to be equal to 1. So if we increase N above 1, then the lift is greater than the weight. And in that case, if the lift is greater than the weight, the aircraft will have this tendency to turn in a circular arc. So before we go into looking at these different maneuvers, we're going to look at how much we can increase the lift by. How much can we do it? Because obviously we cannot just increase the lift to some infinite amount. If we do that, then we're going to break the... Right, something just happened there. My computer fell over, but I was just talking about we can't increase the lift on the wings to some really large, stupidly large amount, because obviously they'll just snap off at some point. So we define limitations on how much lift we can produce, and we define two different sets of limitations. We've got limit loads and we've got ultimate loads, so we'll talk about those. So our load limits are all defined on aircraft in terms of this load factor. So if you guys can recall from 304, which you took with me, and the courses that we took prior to that, if we've got a material component, we can apply a certain stress to it, and it will strain. So we've got the stress-strain relationship, which is governed by the modulus of elasticity of our materials. So after a certain point, the material stops deforming elastically, and we reach this plastic deformation whereby the material is damaged and it won't return to the original linear elastic behavior. Sorry, it won't return to its original position. So for all parts of the aircraft, there is some, or effectively if we can imagine that all through our aircraft, these loads from the wings are propagated through to the fuselage, and there is a value of the load factor at which some part of the aircraft will undergo plastic deformation. Okay, so that is what defines where this limit load occurs. So we say plastic deformation occurs. We don't care where it occurs. We don't think, oh, well, is it happening in the wings or is it happening in the fuselage? We just know that at these limit loads, which we're going to call N with a subscript L, NL, plastic deformation occurs. So if we go over those limits, then some part of the aircraft is damaged to the point that we have to replace it. Okay, so these limits should not be exceeded. We still define some limits above these because we can remember that with materials, I'm looking to see if I've got anything plastic I can break on my desk, and I don't. We can bend things to the point where plastic deformation occurs, but they still don't snap. They actually snap at a higher point, which we're going to call NU, and this is where material failure occurs. So we can appreciate that we never want to reach this one, ever, but we also don't ever want to reach the limit loads on an aircraft. So we define our limits on the aircraft in terms of these ones here, which are our limit loads for a given aircraft. Now, the values of these, the minimum they can be is defined by Federal Aviation Requirements, FAR documentation. I think it's FAR 23. It's highlighted I go over those in the notes pretty well, and it's dependent on the aircraft type. So we'll pick, say for example, an aerobatic aircraft. The loads for these the limits have to be much higher for an aerobatic aircraft. So this has to have a positive NL of at least 6 and a negative of at least 3. So this means it has to be able to produce a lift that corresponds to 6 times the aircraft weight for positive manoeuvres, and it has to be able to produce a negative lift, so a force that will make it go on an arc like this, equal to 3 times its own weight. So these are the limitations of the amount of load the aircraft can produce before the aircraft actually starts to deform in a means that it's going to be unserviceable. So we'd have to come back down, repair parts. So the pilots need to know effectively what these limitations are. And these limitations are important for pilots because we define them in terms of N. We'll often hear pilots talk about them as G limits. Okay, so if we have steady level flights flying along with N is equal to 1, the pilot will feel like they weigh whatever they weigh on Earth. If we have a manoeuvre that has a load limit of 2, so the aircraft is on some circular arc where N is equal to 2, the pilot will feel like they weigh twice as heavy as they do. So they're not looking at these load limits in terms of how much they feel like they weigh. There's what's called a G indicator or a load indicator in the cockpit, and that tells them the load that they're actually undergoing. We don't need to worry too much about that in this course. I'm just relating things back to how they actually occur in aircraft. So these load limits here, NL, these are the ones we're going to work at. We look at their variation with forward speed, and that might sound silly because they're just constants at the moment, but we're going to look at how these limits actually relate to forward speed. And we'll do it in terms of equivalent airspeed, because in terms of equivalent airspeed, all of these load limits are going to be the same at any altitude. So that's why it's useful for us. So let's draw this out. This is my load limit. So we'll put on here N max. Okay, and we're going to plot this versus forward speed. So we're going to plot this against VE. Doesn't really matter about units on the horizontal axis. This is just a qualitative diagram we're going to go through. So for our aerobatic aircraft, we've got a positive 6.0 up here, and we've got a negative 3.0 down here. Okay, these are our limits as defined for our aerobatic aircraft. So we might think, okay, well, we can fly anywhere in this regime then. This would be we can fly anywhere here. We're going to reach issues below certain speeds because we know that actually to produce this much lift, and we've got to recall what happens as we get slower. As we get slower, this line no longer continues to be the limit that defines how slow we can go, because we know the aircraft will stall at a certain speed. So let's remember our aircraft stall equation. So we remember that, I'm going to stop using this colour pen, I don't think the green's particularly good on the screen. Let's try a darker one. So V stall is equal to the square root of 2 times the weight divided by rho s CL max. Okay, so that's our stall speed as defined in terms of our maximum lift coefficient for our aircraft. So we can then rearrange this to get the lift that's being produced. Let's say lift is equal to CL multiplied by half. Sorry, this just comes from the definition of the lift coefficients. That's lift is equal to CL half rho SV squared. We could then say that the lift is equal to N, which is the load factor, multiplied by W. And we can then just divide both sides by W to give us the load factor that occurs at stall. So N stall is equal to CL max multiplied by half rho V squared S divided by the weight. So we've got this load factor that causes the aircraft to stall, or it's the load factor that's present whenever we're at the stall speed. So we can see here this is a quadratic in V squared. So this then can apply a new limit for our aircraft. So let's put this on here. This would be, let's make our 0 a little bit thicker here. No, in fact, let's not do that. Let's just draw our right on the 0 here. And then we've got a limit that's defined by this cubic, sorry, it's not cubic, the quadratic line defining our stall. So we'll call this N stall. And we can appreciate, we haven't necessarily learnt this, that if the aircraft is going to stall at a certain positive angle, it will also stall at a certain negative angle in addition. So there's a CL min, and we can use that to define our minimum as well down here. So in this diagram that we've just drawn, the aircraft can fly in this area here. We can't fly in this area because even though the loads that would be produced at these speeds, at these load factors, are below the limit load factor, the aircraft would stall before these are achieved. So we can say in here, this is stall limited. So at speeds below this one here, this speed which we're going to define, it's not possible to produce loads on the aircraft that are high enough to actually cause structural damage. So it's a really important speed to note, and we call this speed the manoeuvre speed. So here, VA MANOEUVRE. It took me so long to learn the spelling of manoeuvre when I was an undergraduate that I simply can't spell it the American way now. So our manoeuvre speed is the speed at which we've got this intersection of our stall and the limit load here. So we're going to talk about that a little bit. Let's move this over. So we can define the manoeuvre speed in terms of the limit load and the CL max of our aircraft. So this is going to be a single speed. VA is equal to the square root of the limit load multiplied by the weight multiplied by 2 divided by CL max multiplied by the density multiplied by S. Okay, so if we're looking at this in terms of equivalent airspeed, then the density is going to be sea level. If we're looking at it in terms of true airspeed, then the density will be at whatever altitude we're looking at. So we'll talk a little bit about the manoeuvre speed. So we'll say at V below VA, structural damage, I'll put in quotes, not possible. We've got to be careful with saying things like that, okay? So this is purely talking about steady loads due to pure pitching motion of our aircraft. There are many cases where the pilots can be flying, or an aircraft can be flying below VA, and loads can be produced that still cause the aircraft to actually break apart. There was a really famous case. It was American Airlines Flight 587, flying below the manoeuvre speed and encountered wake turbulence. So the pilot put in a series of really aggressive rudder movements, and in doing so caused the rudder to actually shear off. Now, it was attributed to pilot error in that case because they applied some really aggressive loads to the aircraft, but the important part to note was that they were below the manoeuvre speed. So even though we have this tendency to say below the manoeuvre speed you can't pull manoeuvres that will damage the aircraft, it's certainly possible to do things to it that cause a lot of trouble. So let's go back to our plot over here. We've got our diagram that's sort of taking form here now. So this is going to be our VN diagram. In fact, I don't think I called it that earlier. Let's just write that down in big here. This is a VN diagram because we're plotting V and N on here. So we could then, in fact, let's just go ahead a second. I'll start saying now that we think we could fly anywhere in this area here. If you guys can remember from 304 as well, there's going to be an upper limit that we're going to encounter as well. So above certain velocities, then there are loads that occur on the aircraft due to things like due to things like torsional divergence, whereby the wings will have this tendency to twist up until they're going to snap off. There's also flutter that occurs at a certain critical speed, and there's also aerodynamic sort of buffet that can occur at other speeds as well. Now, this introduces an upper limit to our diagram, so let's call this here. This one is VNE, and this is defined separately to the load factors. So this then gives us an envelope in which we can fly, and this is the source of the phrase out of the envelope and in the envelope. We've got one more velocity we can put on this diagram, and we've got the stall speed in terms of where n is equal to 1, so the steady stall. And we already know how to calculate that. This can just go here, Vs, okay, because we wrote that down earlier. So that's stall in steady level flight. So we've now got this area in which we can fly our aircraft. I've drawn this in red, which is maybe a bit silly because red's normally a bad colour, but let's just fill this in. It's more of a pink, I suppose, but this is the envelope in which we can fly our aircraft. So we can see that if we are at flight below VS in steady level flight, the aircraft will stall. If we are in this portion here, so this is flight above the stall speed but producing a load factor, so we're trying to do a maneuver that takes the N above this line here, N stall, the aircraft's going to stall. If we're in here, the aircraft can fly at any velocity as long as the load factor for the limit load is not exceeded, and if we fly up here, then the aircraft exceeds that structural limit load and then will cause plastic deformation to occur at some point on the aircraft. So let's just, have I already shown that? I want to see this line here. I haven't shown how to produce this line here, so let's go through this. How do we work out this line, this curve? Well, let's go through and have a look. So, did I do it? I put stall here. If I did stall, I showed that here. So that's how this line is produced from N stall. We can actually show what this line is here anyway. So this portion where we are below, or in fact this equation works for speeds above VA anyway. We can simply say that N is equal to the limit load multiplied by whatever velocity we're at divided by the maneuver speed, which tends to be an easier means to work out the load limit below VA. So let's just say this. So at speeds below VA, we are stall limited. And then the limit becomes this N here. And then at speeds above VA, we are structurally limited. And then for those case, N is simply equal to whatever the load factor is. Whatever the limit load factor is. And then at speeds where we are above VNE, aircraft can't fly anyway. That's what defines this right-hand curve on here. Okay, so in the accompanying notes, have I got a link to this? I do. In the accompanying notes, this has been updated to go through how to produce one of these diagrams effectively. So this goes all the way through, and I produce all of the code here to produce this diagram here, giving the representative flight envelope. So given an upper limit, NL on here, and the CL max of the aircraft, we can determine the maneuver speed, and we can also determine the stall speed based on CL max, which defines this here. We can then define this curve here. We know NL and VNE will be given as well. So we should be able to produce something like this. Okay, I'll go through an example of this in the lecture on Wednesday, I think. I will go through that together, drawing one of these diagrams, because I'm going to want you guys to produce one of those for your homework for Module 1. Okay, so that was a quick intro to this concept of load limits and maneuver speed. So I want you guys to be comfortable with what maneuver speed is, how we calculate it, what the load factor is, and why we define things in terms of it. And then I want you to be able to produce one of those VN diagrams. If you were given NL, which is the limit load, if you were given the CL max of the aircraft, because you could then define the maneuver speed, and you could also define the stall speed, and if you were given a do not exceed speed, VNE, you should be able to produce one of these diagrams. I would also give you the CL min of the aircraft, which would help you produce that lower side of this curve. So that would help you produce this bit here, going down here. Okay, so all of those accompanying codes are on the website. I want you guys to go through them, try and produce your own, because you're going to have to do something like that for your homework. So I'm going to take a little break, and then I'm going to record a little bit about loops, and then we're going to record about horizontal turns. Okay, I'll see you guys shortly. Hi again, guys. So we've talked about the load factor, which is this means through which we can talk about this increase in load on the wings, or really the whole aircraft. And we can do something like in the background. We've got a loop occurring now, which is a circular path being traversed by the aircraft. We're going to look at two different sorts of loops. We're going to look at the first one, which is this constant radius loop, i.e. flight in a perfect circle. Now, it doesn't look like the loop we've got in the background here. So we're going to talk about where this comes from as well. This is a constant, or something approaching a constant load factor loop. Now I'm going to be using let me start again. I prefer to draw a lot of my diagrams by hand when I'm lecturing, because I think it helps with you guys sort of formulating an image of what's going on. But for this particular one, I am not going to do that, because my hand-drawn aircraft loop images don't look particularly nice. They take a long time to draw, and they still look kind of crap. So instead of that, I'm going to go to one of my diagrams that I just pre-made for this. So I've got an aircraft flying in a loop, and we're going to look at the physics involved in this flight. So this would be our loop entry. I'm probably going to remove some of these later. Now we're just going to look at the forces involved in flying in this perfect circle. So we're going to imagine that the loop is started instantaneously at the bottom. Pilot pulls back on the stick and manages to produce a force that maintains this circular path. So for flight in a circle, and you guys should be comfortable with this from sort of basic dynamics, then our circle has some radius which we'll call r, and so there's also an associated angular velocity which has the symbol omega. And our aircraft has a speed which is v. So this speed is going to be constant in a constant radius loop. So then we're going to, in order to maintain this circular path, the aircraft needs to have a centripetal force, which we'll call Fc. The centripetal force is, we can remember, centripetal means center seeking. This is the one that maintains that loop, and it's what causes the centripetal acceleration, which is what causes us to spin in this perfect circle. So Fc is equal to the mass multiplied by the radius multiplied by the angular velocity squared. This just comes from the definition of centripetal acceleration. AC is equal to r omega squared and Newton's second law. We use those together to get this centripetal accelerator, it's a centripetal force. So we're going to define an angular coordinate as well. So we're going to say that gamma, because this is equal to the flight path angle, is 0 at the bottom, and then we go all the way around to 2 pi. So this is gamma, which defines our path through the loop. So let's go over to the centripetal force. We got Fc is equal to mr omega squared, and then for motion in a circle, we know that v has to be equal to r multiplied by omega. So we can rearrange this to omega is equal to v divided by r. So Fc becomes, I've drawn these as lowercase r's over here, let's change them to uppercase. We can then change this to mr v squared divided by r squared is equal to m v squared divided by r. We can also represent the mass is going to be the weight divided by the gravitational acceleration. So this becomes the aircraft weight multiplied by the flight speed squared divided by gravitational acceleration multiplied by the radius of our curve, or the radius of this circle that we're traversing. So let's have a look at the forces present on our aircraft. I'm going to get rid of some of the writing on here. Let's get rid of loop entry. Get rid of FC. Let's draw our lift on the aircraft. So lift is always in this direction. Okay, it's always going to be towards the center because it's going to be normal to whatever the flight speed is. So we've got lift, 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 and lift. Let's think about the weight. So the weight is acting downwards in this first instance at the loop entry. The weight acting downwards here. Again, we've also got the weight here, and we've got the weight here. So the weight direction changes depending on the orientation of the aircraft. So in order to maintain this total force here, FC has to be the total force present that's pulling the aircraft into this circular arc. So that has to then be produced by the lift, and the lift has also got to overcome whatever the weight vector happens to be at that time, or the component of the weight vector that's acting towards it. So let's have a look at what our lift has to be equal to. The lift has to be equal to that centripetal force that's produced to maintain the circular arc, plus the weight multiplied by cosine gamma, where gamma is the position through the loop. So we can appreciate that it's 0, the loop entry, this is equal to 1, so it's equal to FC plus the weight. And then when this is at the top of the loop, it's going to be FC minus the weight, and at the two other positions, this is going to be equal to 0, so it's just going to be equal to FC. So we've already got this expression for FC. We can just replace that. We've got W multiplied by the flight speed divided by gravitational acceleration and the loop radius. Okay, so we have this expression for lift. We can define this in terms of the load factor now. So N, remember, is equal to the lift divided by the weight. So for our aircraft, it's just equal to the aircraft in the loop. It's equal to V squared divided by GR plus cosine gamma. So this is our load factor variation in a constant radius loop. So from this and the definition of the load factor that we have previously, we can define the minimum radius. So we can see here that the radius, if we were to rearrange from the radius is going to be inversely proportional to the load factor. So for the maximum value of the load factor and the combination of the flight speed is going to give us the minimum turn radius. So let's rearrange this for the radius. So we've said for the constant, so the expression we've just done is in general the radius for a aircraft in a loop, but for the constant radius loop, this is going to have some minimum value, and the minimum value is going to be at where this is at the bottom of the loop, because at the bottom of the loop, this is going to be equal to 1, which is going to mean that the load factor is then going to be limiting our loop here. So this then defines the minimum radius of our loop. And I've jumped ahead a little bit there because actually I've said at the bottom of the loop where we've got cosine gamma is equal to 1, we want to have the minimum value of v squared over n. And this occurs at the manoeuvre speed. So we can see here that the minimum radius for a constant radius loop is going to be at the manoeuvre speed, and it's going to be a function of the manoeuvre speed and the limit load minus 1. So this is because that's the defined at the position of entry. So that means that upon entry to this loop, at the very beginning where we've got this instantaneous control application to produce this load factor, the stick's pulled back on and we've then instantly gone to the maximum load factor. Now, because our actual load factor in the loop is defined, let me find it, because our load factor is actually defined by the position, because it's the function of gamma there, we can see that everywhere else in the loop the load factor is actually going to be lower. Okay, so that load factor is going to be lower everywhere because at every position this is going to be less than 1 except for the bottom of the loop. So this is why, in general, the loops tend to look more like this sort of teardrop shape. We can appreciate that a constant radius loop is also meaning the pilot's going to have to constantly vary the angle of attack of the aircraft to maintain a varying lift during the entire loop. It is going to be easier for the pilot to maintain a constant load factor in the loop. So for a constant load factor loop, it's going to look more like this, and we're going to define the equations that give us those different load factors. So we can bring back the expression for the radius as a function of the load factor. R is equal to v squared divided by g n minus cosine gamma. So if we now can allow the lift to increase beyond the loop entry, so if at the bottom of the loop we're at the manoeuvre speed and we're producing the maximum load factor, that defines the starting radius. Once the aircraft changes its orientation, so there's less weight effectively being supported by the lift, some of it starts to be supported by thrust instead, then the lift can increase as well. So that therefore increases the load factor that's possible, and that's therefore going to increase the denominator on here, which is going to reduce the radius of our turn. then we can look at tabulating the radius at different parts. So let's say for different gamma, which is our loop position, we can define the radius. So it's 0, which is the loop entry. We've got pi on 2, which would be a quarter of the way around the curve. Pi, which would be the very top of the curve. And then 3 pi on 2, which is a quarter of the way back down again. So let's keep our expression up. We've got VA squared divided by G NL minus 1. Here we've got VA squared divided by G. Now cosine gamma of pi on 2 is equal to nothing. Here we've got Vn squared divided by G NL plus 1. And then here we've just got the same load as before. So we can appreciate that the denominator is largest here, so we're going to have our lowest turn radius. So this is min radius. And then our maximum radius, we already know, occurs at the entry to the loop. So that's why our loops tend to look more like this inverted sort of teardrop shape. So we have this low radius decreasing up to the minimum, and then we've got this loop continuation down here. So what we effectively have, we're drawing a circle whose radius is continually decreasing up to the top, and then it's then increasing again. You don't need to worry too much about the actual shape of these. What I'd like you guys to be able to do is just calculate the turn radius at different positions. If you want to calculate the actual what these loops look like, it's a slightly more involved calculation. I borrowed a methodology from a source online, which I've cited at the top of here. I go through a numerical calculation to look at the constant load factor loop and what it looks like. So again, I want you guys to be comfortable with sort of qualitative questions about what the load factor occurs at different parts of the loop, and also, some quantitative as well. So looking at calculating what's the load factor at given parts of the loop, because this is going to be dictated just by the manoeuvre speed and your load limits here. So that's our loops looked at. We're going to move on to look at steady turns now. Right, so we're going to move on from loops. We're going to consider turns. So if the aircraft wants to go in a direction that maintains constant altitude, but where we fly in a direction that changes heading. Now, again, we're going to look at purely circular motion. So for this case, the aircraft is no longer flying in a circle in this direction, but the aircraft needs to fly in a circle horizontally. So very similarly, there needs to be some sort of side force being produced by the aircraft. Exactly the same, it's going to be the FC, that centripetal force being produced. So there's two ways we can do this with an aircraft. The first one is the way that most sort of undergraduate aerospace engineering students think is, well, we'll just use the rudder. We use the rudder, we'll deflect the rudder, and this will produce a side force that is towards the center of our turn and will cause the aircraft to turn like this. And that's one means that a turn can be performed. It performs what's called a flat turn. It's a couple of reasons why we don't like to perform turns like that in aircraft. Firstly, the rudder's not really for that. The rudder's there to produce side slip on the aircraft or to control side slip. So if a turn is flown by using the rudder causes the aircraft to side slip, which means the entire duration of the turn, the aircraft has got a velocity that's going in this direction on the fuselage. So that increases the fuselage drag, which causes more thrust to be required in order to actually just maintain steady flights. So it's inefficient. Also, the rudder's pretty small in terms of its size compared to the lifting surfaces of the aircraft, which means that it can't produce much of a force. Also, if the aircraft flies along in this sort of motion, this flat turn, then the centripetal force is going towards the center, which is the one that produces the turn. The one that's perceived by the pilot and any occupants is called the centrifugal force. Now that's the reaction that actually causes you to be pushed to the side of a car when you go around a turn, and it's the one that's sometimes called this fictitious force. I don't like the expression fictitious because it's real. It happens, and it just happens when we've got a frame of reference that's moving with respect to another. But that centrifugal force is quite unsettling. It means that the pilot is going to have to fight to maintain this seat upright, otherwise they're going to feel pushed, or they will be pushed in the direction opposite to the turn, and it's not very comfortable for any passengers. So we don't really ever feel that during flights we've been on, do we? So we know that this isn't the mean that turns are produced on those sorts of aircraft. So we tend not to use the rudder for them, and we've argued why we shouldn't do it, and the fact that you never really feel that during a flight on a passenger aircraft means that we know it's not how they're produced. Also, they don't look very cool. Okay, a flat turn like that doesn't look particularly cool. What looks better, I think, is a turn like this. So what's called a banked turn. So this is an F-15 in the Mark Loop in Wales. So this is a US Air Force F-15 doing a loop through a valley in Wales called the Mark Loop, which is an amazing place to go walking because you can just see aircraft like this. Some of the pilots of whom I actually used to know through my wife, which is amazing to see them flying. So rather than producing the side force from the rudder, what happens now is the aircraft banks through the bank angle, which we give the symbol phi, and then the lift is now in this direction. So that means part of the lift is working in this direction. So we're going to use that to produce our turn, and the reasons why we do that we're going to go through and produce some diagrams for. So we're going to look at banked turns. So in general, for all turns, we want to produce this side force. So let's just write this out now. This is my terrible aircraft diagram, but where we've got our flight speed, v in this direction. Again, we're going to want to produce a turn of radius r. It's going to have some angular velocity omega, which means there has to be this force being produced Fc. So in a banked turn, the aircraft is rolled through this angle phi, which gives part of the lift producing Fc. So we tilt the lift vector, which means the part of the lift vector is now producing this side force. So let's draw what this looks like. Aircraft wing is now at this angle. Fuselage is hanging underneath it. This is a terrible drawing, so let's make that slightly bigger. And let's say that this is the force we want to produce, Fc. This is an aircraft that we're going to say is flying towards us, so let's draw our cockpit in there. The lift is being produced in a direction that's parallel to the aircraft up direction effectively, but being normal to the aircraft flight speed. So that's the lift. The weight is still acting downwards. So this now means that this component of lift to maintain steady level flight has to now be larger to overcome the component of weight. So this part here is L. Let's just draw the bank angle in phi. This is L cosine phi in this case, which means this part here is L sine phi. So we can immediately see that the lift has to be this addition, it has to overcome the lift that was produced previously in order to maintain this vertical equilibrium. And we can see here that L cosine phi has to be equal to the weight in this case. That's what enables the aircraft to stay in the same vertical plane. That's to maintain constant altitude I've just written. And remember, our definition of the load factor is n is equal to L divided by W. So we should be able to see here that cosine phi is equal to 1 over the load factor in this case. So for a higher load factor, effectively we increase our bank angle. And we can relate this back to the FC, and we remember FC has to be equal to, I've got to check, equal to mv squared divided by r in this case. That's the turn radius that we need. So we can then relate that back to the bank angle, and we can then look at this in terms of the things that we need. So just by looking at forces in the horizontal components here, this part here has to be equal to FC. So to produce the centripetal force, L sine phi has to be equal to m v squared divided by r. And we can then represent L as NW in this case, and we can do some manipulation of this to get an expression. Remember before we said M was equal to W divided by G, so we're going to say NW sine phi is equal to W V squared divided by G multiplied by R. So this gives us an expression which is relating our turn radius to our bank angle in this case. So we can then come up with this expression. So we can look at 3 different ways that help us represent V squared on R, because this is going to tell us things about our turn performance. Because this bit is what we want to know. So we can represent that in a few different ways. We can see the W's are going to cancel in here. So we can say that the first one is just V squared on R is equal to NG sine phi. We can also use the definition of we can just look at the angles, and we can look at the definition of, remember that n is equal to inverse cosine of, sorry, not inverse cosine, that's bad nomenclature there. Let's say it's equal to 1 over cosine phi. So that's also therefore equal to G multiplied by the tangent of the bank angle. And through a little bit of manipulation we can also change this, remember, from sine squared phi plus cosine squared phi is equal to 1. We can rearrange that into sine phi is therefore equal to the square root of 1 minus cosine squared phi, which is equal to square root of 1 minus 1 over n squared. I'm having to do this in my head because I haven't got notes prepared for this. So we've got that expression. We can substitute this into here and then take the n inside the brackets to give us, this is going to be G multiplied by the square root of n squared minus 1. Okay, so we've got 3 different representations of the turn here that give us the radius as a function of the relationship between the flight speed and our turn radius. So what we care about with these turns is how tightly can we take them. So we're going to look at an expression for the radius now. So we want to know the minimum turn radius often, because that dictates whether we can get around certain obstacles, for example, or how effectively the space needed to turn around an aircraft. So we can take one of those expressions and we can just substitute the lift for the weight, and then we can use the definition of the lift coefficient. So we can say that R is equal to 2W divided by G rho S CL sine phi. So this just comes from using the expressions that we've got up here and then substituting the velocity from the lift coefficient into these expressions. Okay, so I'd like you guys to try and show this and tell me on Slack if you have any problems with that. So you're going to put that on Slack. If you can't do it, the things that are going to help you remember, the lift is equal to the weight, and that also we've got the definition of the lift coefficient. CL is just lift divided by the dynamic pressure and wing area. So we can use those to get that there. But from this expression, we can look at a few observations about the turn radius, and we can see that for a given turn, the heavier the aircraft is, the larger the turn radius has to be. We can also see that the smallest turn radius is going to be the largest value of CL, so it's going to occur at CL max, and it's going to be proportional to the sine of the bank angle. So the largest this can be is 1, which is going to be at 90, which is why in a turn that looks like this, we can see that's a tight turn occurring at a very high bank angle, or a very steep bank angle. We can look at the other things that are going to minimize the turn radius. For minimum R, we're going to want the maximum value of density, so that's going to be occurring at high altitude. And we also want to have effectively large wing area, so an aircraft with a low W on S, so let's draw that out. W on S, which defines our wing loading. So a small value of wing loading gives us a larger, a small value of wing loading gives us a smaller turn radius. Small wing loading gives us a small turn radius. So that's defining our different ways that we can calculate banked turns, and I spoke about flat turns and why we don't use them, but what we calculated there is conditions that give us the turn radius based upon different things. So for a given aircraft weight, you should be able to see that for a certain altitude your turn radius is going to be given by the stall CL, and you can work out the bank angle is then going to be proportional to the load factor as well. So remember, from here we've got, it's going to provide another limitation on this one. So in class on Wednesday we'll do some numerical examples about determining the minimum turn radius, but this has gone through a lot of the theory. We've gone through it quite quickly today because I wanted to get this lecture out fast, and hopefully that's been a good introduction to the definition of load factor, what a VN diagram is and how we produce it. And we've looked at loops and we've looked at turns. So we've gone through motion in a circle for an aircraft in both the vertical and the horizontal plane. And this has nicely brought module 1 up to a close. We'll go through a review on Wednesday and we'll go through more numerical examples before your big test. I hope you guys are having a wonderful weekend, and I will see you all